Okay, welcome everybody, and so welcome to this this week's HIT seminar. And our speaker today is Jorge Noronha, and Jorge essentially got his PhD from Frankfurt University in 2007. Yes. And afterwards, he was a postdoc at the Columbia University with Miklos until 2011. From 2011 to 2019, and he was a professor at São Paulo University. And since 2019, he joined University of Illinois at Champaign as a professor since then. So we are very glad to have Jorge here today, and he will give a talk on hydrodynamic frames, the good, bad, and the ugly. So we'll see who wins. Go ahead.
Okay, thanks a lot for the kind introduction, and thank you for Shenyang for the invitation. It's also very nice to see some old friends and colleagues here. And hopefully next time we'll be able to visit there in person. So today I'm going to talk about this thing, hydrodynamic frames. And some of you may know what that means, but I hope that by the end of the talk, you understand what are these different frames and how is that related to hydrodynamics, and how that is actually connected to how we understand hydrodynamic behavior, both in heavy ion collisions and in neutron star mergers. Oops, sorry, guys. Okay, so this is a talk about fluid dynamics. And one thing that you will appreciate is that fluid dynamics is everywhere. And it's not only everywhere around us we have fluids, but why is fluid dynamics so important and so ubiquitous in our description of nature? It's because it's based on very general principles, very general things like conservation laws, for example, conservation of mass in the normal relativistic regime, or conservation of energy momentum. And also the hypothesis and also the assumption of large separation of length scale. So what I mean by that is that in general, when you try to describe a certain system as a fluid, is because you have some scale that you call macroscopic scale, capital L, as you can see here, and some little scale microscopic L, this little L here, which, for example, for a gas would be associated with the mean free path of the particles that collide once in a blue moon here in the gas. And usually, the way to describe a certain system as a fluid, it will be related to this quantity that we're going to call the Knudsen number, which is the ratio between the micro thing, the small, to the large. And when this number, which is like a field actually in descriptions that you do with calculations, when this thing is much smaller than 1, we call this a fluid. That's why, even though we have little molecules colliding here in the air, we can describe, every time I move my hand here, with a very good approximation using fluid dynamics, describing the motion of the flow velocity of this fluid here. And you see this, and fluid dynamics is applied in different cases, such as, for example, the motion of a hurricane here on Earth, and also the flow of the car, of the air past this car. But what I'm interested in is really the frontiers, the extreme of fluid dynamic behavior. First, in the lab, as you will see here, that will be the case of ultra-relativistic heavy ion collisions, where now the big scale, the macroscopic scale, is kind of tiny. It's scales that are related to nuclear or even particle physics. And at first, not only just the nucleus, but also the proton itself. So one question that you could ask is, could you have experiments where the proton itself displays some liquid-like behavior? So this sort of defines the frontier of the knowledge that we see now in heavy ion collisions. The other frontier, going from the micro to the macro, is fluid dynamics behavior in the sky. In this case, when you have fluid dynamics under very, very strong gravitational and electromagnetic fields, as it appears in neutron star mergers. So here, there's a simulation shown in this paper where they have the collision of 2 neutron stars, and on this side, you have the temperature field in MeV, and here the density for this type of configuration. So we'll see my talk here is going to go through both extremes. So first, let me talk about the frontier defined at very, very small distances, for example, in heavy ion collisions. One of the fundamental properties that we have learned over the last 2 decades is that the quark-gluon plasma formed after the collision of heavy ion collisions seems to behave as a strongly coupled fluid. And it's a strongly coupled in the sense that the coupling between the quarks and the gluons is not really necessarily small. Some number that we cannot really yet precise, but at least from extractions of model calculations of hydrodynamics with in comparison to that to data, we can see that the shear viscosity to entropy density reaches a small number. So it's a number smaller than, of the order 0.2, which if you compare this to water will be of order 1. So it's a very, very strong, strongly coupled system and also a very good fluid. And over the last 2 decades, there were several calculations. This is just one example of them, as you can see here on the left-hand side, where we showed that comparisons done with hydrodynamic models that describe the anisotropic flow of hadrons formed in the collision. When you compare the models to the data, so this is from Atlas data, you see that there's a good description for different ways that the collisions happen, in this case, different centralities, for a given small value of this 8 over S. So the overall picture is that this QGP, the quark-gluon plasma, is formed and it behaves like a fluid, but not only just a fluid, it's a relativistic fluid. So the velocities involved are close to the speed of light. So, but how does one describe fluid dynamics in this relativistic context? Well, the first thing that you do, as before, you rely on conservation laws. So for example, here you have the conservation of energy and momentum. That's what the symbol here means. So this tensor here is the energy momentum tensor. It tells you what is the distribution of energy in your system. Also, what is how much momentum you see in a given direction, how much energy you see flowing in a given direction, and also the pressure, the shear stress, the momentum flux. All of that information is contained in this symbol here, in the energy momentum tensor. And normally what you do is the following. So you say, oh, okay, so I have a fluid. I can separate the amount of energy momentum that comes from ideal hydrodynamics. So this is the approximation when entropy is never produced, which is this part here. And we separate that from the dissipative part, the viscous part. That's what this symbol here means. And here, the quantities that you see here, this is the energy density, this is the pressure, defined by the equation of state. That's why there's a little epsilon here. And this u mu is the flow velocity, the forward velocity of the fluid in this relativistic system, where in g mu nu here is just the metric. Okay, so this is just standard textbook stuff at this point, but what about heavy ion collisions? Well, at first, I would say before 2010 at least, it seemed that hydrodynamics was really justifiable. At least, after the experiments around 2000, coming from the relativist heavy ion collider. And the overall reasoning was the following. Remember, we are supposed to describe hydrodynamics when we have some large separation of scales. And at first, if this is the picture of the energy density of the QGP, you see a very smooth distribution defined here in this transverse plane. So the beam direction will be in the Z direction here, and this is X and Y. In that case, spatial gradients are very small, and then you'll have gradients of the order of 1 over capital L. The microscopic scale would be of the order of the temperature. So if you condense those two and try to estimate what this Knudsen number would be, it'll be something of order 0.1. So for a system that is very, very smooth like that, it is justifiable and reasonable to try to apply fluid dynamics at scales of the size of a large nucleus. However, as always, reality is much more complicated and interesting because it turns out, driven by experimental findings, for example, triangular flow, we know that the inherent quantum fluctuations that appear in the initial state of the collision of these heavy ions is actually not really something that makes these things really uniform at very, very large, at all scales. So for example, you do have fluctuations at least of the size of a proton itself, at least of 1 Fermi size. So the energy density looks much more inhomogeneous than before. So it has peaks and valleys. So this comes from this from the unavoidable quantum fluctuations that we have in the system. And also, and this is very important, the presence of very large spatial gradients at very early times, right after the collision. So it turns out that if you try to estimate this Knudsen number, to see if it's much smaller than 1, it turns out that it's in general not. It depends on how you choose for the transport coefficients, at what time you choose for the initial condition. But in general, this Knudsen number thing, so this thing that it tells you whether at first you should think about a hydrodynamic description, is not really a small number in heavy ion collisions. So this sort of gives you a paradox, because the Knudsen number is not really small, it could even be large, but somehow hydro, and here I put in quotation marks because hydro is not just a little mod, it's a whole framework to compute observables, for example, in heavy ions at very low momentum, but hydro itself still works. This issue must be understood, okay? So we have to think about these conceptual issues to actually really make progress and make sure that the things that we are computing are really the things we are supposed to be computing, and whether or not the approximations that we are making really make sense or not. I think we are in the phase of heavy ion collisions now that is not enough just to blindly apply the models. We really have to think very deeply what's going on, especially when it comes to hydrodynamics, because we've been applying this to at earlier times where the gradients are larger and larger. So let's talk about the unreasonable effectiveness of hydrodynamics in heavy ion collisions. So one thing that has been very clear is that as one decrease the system size from large nuclei to PA and even PP, as you keep decreasing C here, you see that what you call big is now getting very, very tiny, not being much larger than the size of the proton itself. So of course, as we do that, we increase the theoretical uncertainty, and we really probe the regime of applicability of hydrodynamics in a way that it was never done before as we go to smaller systems. So there are several questions that comes to mind. So for example, when does this system stop behaving hydrodynamically? Does it ever stop to behave hydrodynamically? How does, for example, quantum entanglement affect the onset of hydrodynamics? I mean, these are not little balls colliding. These are quantum color fields here. So how does entanglement play a role in the emergence of hydrodynamics in heavy ion collisions? And the question that I'm going to address here, at least in the first part of the talk, which is actually much easier to answer than the other two, is whether there are fundamental constraints that must be fulfilled in order for us to really say, look, I do have some hydrodynamic behavior and it makes sense and so forth. So these are the things that I'm going to first talk about in this first part of the talk. So what goes into these famous relativistic viscous hydro simulations of heavy ion collisions? So you see here some very nice little animation from Bjorn Schenker. Here you see the ideal fluid, and here a viscous fluid. One thing that you can see, once you don't have any viscosity, structures are preserved at later times than in the case with viscosity, that things get diffused and less well-defined as a function of time because of the effect of viscosity. So one thing that you should always keep in mind is that every single viscous relativistic hydrodynamic simulation that you have ever seen in your life in heavy ion collisions always use ideas that can be traced back to Israel and Stewart. And this thing, in this fundamental paper, was written in 1979. And I'm going to explain to you very, very briefly what is the main idea here. Forget about the equations. Just think about what's going on here. The point is the following. In order to describe a relativistic fluid, what Israel and Stewart realized is that not only you would have to solve for the standard hydrodynamic fields, for example, temperature, flow velocity, chemical potential, but also that the dissipative quantities themselves. So this is these two things here. This is the shear stress tensor and this is the bulk scalar. These are quantities that tell you how much the system deviates from equilibrium. So the point is that in their theory, in the Israel-Stewart theory, the prevalent theory that is used everywhere in heavy ion collisions, when one solves the equations of motion, you have equations of motion for the hydro variables and also for these other variables. And the way they work is the following. Not only you have energy momentum conservation, but you also have extra equations for these variables. And they have more or less this format of nonlinear relaxation equations like this. So the pi, for example, the bulk scalar will relax towards a limit that we can talk about later. The same thing for the shear stress. So you have to solve hydrodynamics. By solving hydrodynamics, we mean solving a bunch of partial differential equations that are nonlinear and have to be solved many, many, many times. So you see that there are many, many terms, there are many, many, many coefficients. And at least in this case, if you just have one single chemical potential, have 14 coupled nonlinear partial differential equations to solve. This is hard stuff to solve, but collectively over the years, the field through many different groups has learned how to solve these things. And that's one of the biggest achievements that we have in the field of heavy ion collisions that is now being transferred to other fields, for example, numerical relativity. But my question here is, are there fundamental constraints that must be fulfilled? So for example, you can think about very, very simple things. Thermodynamical consistency should be one of them, should be a key thing because you want to do things that are thermodynamically consistent. Another thing is if your fluid is a relativistic fluid, and you're supposed to solve this in relativity and maybe even general relativity, you must have that your fluid dynamical equations preserve causality in the sense of relativity. So it should be a causal evolution, okay? And also, I mean, just because we are not crazy people, the equations of motion are complicated, but they should have solutions. And the solutions, that's what I'm saying here in the second part, the solutions should exist and be unique. By that, I mean, for a given set of initial conditions, the evolution is well defined. And in principle, if you have a code that is good enough, you should be able to solve it. Those are very simple things that should be done. Yes. Is there a question?
Yeah. Sorry, I started clapping instead of raising hands. Okay, I just wanted to ask a few questions here, not trying to make any blasphemy or anything, yes. But let's consider causal part. So what can be acausal? The equations themselves can be acausal, right? And the equation of state can be in principle acausal.
Yes.
Right?
Yes.
So what is going to happen if one of them is failing and another of them is fine? What will happen if both of them, like what will the failure look like?
Yes, so there are several things that can happen. So first, for example, if you have equations that are not hyperbolic, at some point you'll see that information in your system is not really propagating as a wave anymore. And it violates the speed of light. For example, this is something that we're going to see here soon, that for example, the actual velocity of propagation of information in your system should be bounded by 1 in natural units, should be bounded by the speed of light. The other thing that does happen, if you have a system, for example, that is acausal, what you can prove, and this has been rigorously proven, is that stability is not a Lorentz invariant concept, which is weird, right? You would think that if the system is stable in the sense that, if I see the system having a stable evolution, and if I just boost myself to another Lorentz frame, it's, this cannot make the fluid explode or anything, right? And that's true, but this only happens if the system is causal. If the system is acausal, you break time ordering, and different Lorentz observers will experience something completely different. They will actually see, for example, that solutions will diverge and equilibrium is not going to be stable anymore. I'm going to talk about
so are you saying that in some frame you solve it and it's fine, and then you boost to another frame, you solve it and it's crazy and it's blowing?
It's more like this, that if the theory is acausal, instead of seeing fluctuations that decay towards equilibrium, I'm there, and out of the blue, something pops out and it starts growing like crazy.
I see.
It never dies again.
Thanks.
Yeah.
So what about equation of state? Suppose you have perfectly causal, nice fluid dynamics, but problematic equation of state.
Yes. So, for example, let's remove all the viscosity and everything that makes things complicated. I'm going to talk about this here. But if you have just simple ideal hydro that is completely described just by the equation of state, if you remove causality from this, then other issues can appear again. So you would have stability problems. And the other thing that I cannot ensure is whether or not the solutions that you have from your theory are unique. So you could have, for example, 2 different initial conditions leading to exactly the same evolution, which is strange. Or better, imagine that the system is evolving, at some point it just bifurcates, which is weird. We shouldn't have that.
So for the case, for example, we are looking for a phase travel.
Dima.
Okay.
Dima, I have to go.
Just
otherwise,
leave the long question at the end. Okay.
Sorry.
If you have short question, you can
Yes.
drop. Long discussion probably should leave that.
Yes, I appreciate the questions, and we can go through them afterwards. Going back, what are the fundamental constraints? So these are just two, and I'm going to see the effect of them now. So for causality, this of course is an essential property of relativity, and basically says that the information or the whatever happens in a given point cannot, you don't have information come from every single other part of space and time. It's just some finite region that can propagate and give and alter the physics at this particular point. So that's the idea of the light cone. And if you have, for example, if you do this in general relativity, the light cone will be a little bit distorted because space-time itself is dynamical, but the idea is still there. Still have the relation of cause and effect, and information at this point can only come from some finite region. The other property that I said about solutions and stuff like that, normally mathematicians call this well-posedness. And the idea is just that if you have some system of PDEs, the system will be well-posed. If given some initial data, you can show that a solution exists. So you are okay solving these equations. And the solution is unique. And this is the minimum that people should require for solving an equation. And normally in physics, for the good equations, the ones that we really understand, people have proven this before. So that's why we normally don't think about those issues. But if you just invented some new equations out of the blue, you should think about that because you want to have equations that can be solved. And also the solution depends continuously on initial data, because if you change a little bit the initial conditions here, you want to be able to propagate that difference through the solutions. So these are general requirements that are present in mathematics, but they're also very physical, right? So we want to work with theories that have these properties. So what about the equations of motion currently used in heavy ion collisions? Well, when I say that it's just energy momentum conservation, there's a bunch of little symbols that go into that. There's the conservation of energy momentum. But also these other equations for the dissipative fluxes that I got here from this DNMR paper, as you can see here, it defines several different coefficients, not only the bulk viscosity or the shear viscosity, but also the relaxation times for bulk and shear and a bunch of other transport coefficients. All of these equations are currently being solved in heavy ion collisions. And over the years, the field developed the necessary numerical techniques to really solve these equations very accurately. So the questions are, what are the general properties of these equations? Not just when you're very close to equilibrium, but even when you're far from equilibrium, as it happens, right when you switch from your initial state model that could have some elements, for example, of glue and saturation, to hydrodynamics, right there in the beginning, where the gradients are very large. What are the properties of these equations? These equations make sense there. Are these equations causal in this non-linear far from equilibrium regime? And are the solutions okay? Are they unique? Do they make sense? Can you actually solve these things reliably? So one thing that you may wonder is like, okay, man, people should have done this. I mean, this is from 1979. And in fact, Israel Stewart themselves, they showed these properties only in the case when you have the system very, very close to equilibrium. So imagine that the system is here, this is equilibrium, and you put a very tiny linear disturbance around it, and they showed that these equations will be fine there. But such results, they're well known in the literature and implemented in every single hydrodynamic code that you can possibly see. Such results say nothing about the theory in the far from equilibrium regime probed in heavy ion collisions, especially at early times. And in that case, what you actually see is that deviations from equilibrium are very large. They are of order 1. So this is the pressure coming from viscosity, and this is, for example, just forget about the epsilon. It'll be just comparing the contributions to the pressure, one from viscosity and one from ideal hydro itself. There are constraints on this far from equilibrium hydrodynamics. And luckily, there are new constraints about that. So this is a paper that we published last year in PRL, where we, for the first time, derived the full conditions that ensure causality in this non-linear far from equilibrium regime, including shear and bulk viscosity effects. The constraints are extremely complicated, as you can see here, a bunch of different inequalities, but what do they mean is the following. They just tell you, and they just define how large or how far from equilibrium you can still be. So how large are these contributions in order for you to still have some meaningful evolution. For example, that you're really solving well-defined hydrodynamics, not some other crazy thing. And the new thing about these conditions that were never really done before is that they are valid in the full nonlinear regime. There are no approximations here. So these new constraints allow us to determine how much we can trust, how much we can push hydrodynamics towards this very far from equilibrium regime. But they also lead to many questions, right? So for example, this hydrodynamic framework provides a very good description of experimental data. We have known this for 20 years now, but considering especially the last, state-of-the-art simulations, are our simulations truly consistent with relativity? What I mean is the following. Can we ensure that when we are solving these things numerically, we're really having a system that is causal, the solutions are well-defined, and etc.? Are there issues with causality in the state-of-the-art simulations of the quark-gluon plasma? And the answer, unfortunately, is yes. So this is a paper that we put out last year. Shun Cheng and his student also had a paper at the same time, where we investigate this, whether causality violation happens in state-of-the-art simulations. And these are open source codes that we can just download, for example, music or Vishnu. We can download these things, and we have done this. So this basically shows evolution. Let's just focus on the first case. So this is what happens. So the initial condition is done by IP Glasma, and then we couple this to music. This is something that we have used in the field for quite a long time. Red means cells that are acausal. Blue means cells that are fine. They're all causal. Everything is fine. Don't worry about it. And purple are cells that we cannot answer whether things are well defined or not, or whether causality is violated or not, using the conditions that we have. So as you see here, because we push hydrodynamics to work at very, very, very early times, where deviations from equilibrium are huge, most of the system starts acausal. And the evolution only really start to have well-defined causal behavior at around 4 Fermis or 5 Fermis or so. We have tried this with different codes, different types of initial conditions. And basically the overall result is that up to 75% of the initial cells are really acausal in state-of-the-art simulations. Those are the type of simulations that we use to extract, for example, transport coefficients from Bayesian analyses. And the superluminal propagation is of the order of 20% larger than the speed of light. So there will be cells where if you compute the propagation of information there, it's going to be larger than the speed of light by 20%. This is an issue that must be investigated, and we are currently thinking about how to fix this problem. One of the things that we found, for example, is that what you do for the initial state really, really matters. And I think that's the key to take from this work. This is not necessarily a criticism of hydrodynamics per se. It's just better understanding when you can actually apply hydrodynamics, given that it's a fundamental question in the field when the system transitions from some sort of coherent state, gluon-dominated field towards something that looks like a thermal system in equilibrium. We found this weird behavior in all open source simulation packages that we tested. And this is not a numerical issue, okay? This is very important to stress. This is not a numerical issue. This is not because the codes are bad. No, the codes are actually very good. This is a physics issue. Because, for example, if you start with a very nice initial condition that is smooth enough, no problem, everything is fine as it should be. This is a physics issue. We are just mapping and starting hydrodynamics at too early times. And one thing that we found is that, for example, if we include some different models for pre-equilibrium behavior, for example, the compost model derived in this paper here, it actually reduces a lot the number of acausal cells, but does not eliminate the issue. So I think there is some fundamental structural issue here, that is pointing us towards precisely the mapping between the initial state and the beginning of hydrodynamics, which has always been interesting, but I think now it's a very, very clear issue that should be worked on, and I think deserves the attention of the field. But the way I see this is that I see this as motivation to reaccess the foundations of relativistic hydrodynamics. So these are challenges, but not just challenges, these are opportunities that I think we can pursue as a field in the future. And as you know, heavy ion collision sort of defines the state of the art of what constitutes viscous relativistic hydrodynamic simulation. So I think it's only natural that we start to go beyond and really define what the field is. So I think this type of studies, they're really sort of the cutting edge of what constitutes hydrodynamic behavior are needed. And I think they will be important for other fields in the future, not just for us. So let me now go to the second part of the talk. Now we stop with the micro, the little things in the heavy ion collisions. We go to the big things at kilometer size scales in neutron star mergers. And one of the things that you see here, this is a simulation from this paper that we worked together with many people here from different institutions. You see what happens with the collision of two neutron stars. And there are different regions here that tell you how large we expect bulk viscosity corrections, for example, to be large as you keep varying the scale of the simulation. The scale of the merger here is in milliseconds, and the things first. So this is before they collide. So they collide, they form some complicated matter, and then this matter oscillates, and the bulk viscosity damps these oscillations. So are viscous effects important in these binary neutron star mergers? So these are questions that people have been thinking about in the field for years. And this sort of picked up in 2018 after this paper, where they showed that, or better, they estimated that bulk viscous damping would be relevant in neutron star mergers. So basically, the matter, the two stars collide, they form this very complicated hypermassive remnant. And this thing sort of has oscillations, so it has density oscillations here. And these oscillations are such that the energy density gets out of phase with the pressure. And that is basically what bulk viscosity is. And what these people here have computed is they have computed what would be the size of the bulk viscosity. And this depends on many, many different things. It depends on the type of equation of state that you have for the nuclear star matter, the neutron star matter, depends on the density, depends whether or not neutrinos are trapped or not, depends, which is also related to the temperature, and also the type of frequencies that are accessed in these oscillations within the neutron star merger. So what we did in this paper here, published last year, we did a different approach. So we used state-of-the-art ideal, so there's no viscosity in the simulation, ideal fluid simulations in general relativity. So those are the things that you see here. And what we did, we estimated the effects, what we call here in, using this probe limit. So basically is the following: this bulk viscosity here would be proportional to the gradient of the velocity. And we compute that gradient using the velocity given in the ideal case, okay, just to estimate the size. And depending on the equation of state and the type of particles that you have in your equation of state, the bulk viscosity may be relevant in the post-merger. And one thing that we realized, and we made this plot, is that we can compare the typical size of these quantities on average, okay? So this is not just locally, this is on average, this is integrated over the whole system. In heavy ion collisions, which is the red, and neutron star mergers. So you see, in neutron star mergers, this quantity is smaller than in heavy ions. We expect that, but it's non-zero. So it'll be interesting to actually do a full-scale simulation. By that I mean, don't use ideal hydro in general relativity. Go there, change the equations of motion, and put this bulk viscosity guy and evolve it all together and see what it looks like. So what awaits us when we combine fluid dynamics and general relativity, not just special relativity, but now general relativity. Space-time itself is dynamical. Well, that's what we get. So for many years, there was a fundamental roadblock that really prevented any progress in this systematic evaluations of the effects of dissipative quantities or fluid dynamics in general relativity. And the issue is the following. So why is this so challenging? Some of you may have heard about this before, but some of you may be just hearing this now. So please realize that not everything is done in this field. Einstein's equation has been around for a long time. Fluid dynamics, even for Israel's Stewart case, has been around for a long time. But the problem is that the equations, Einstein's equations plus the fluid dynamics, they are highly nonlinear equations. Those things are hard to solve and hard to understand its properties. And previous approaches to describe viscous fluid dynamics were either acausal or unstable, are not really known to have well-defined solutions. So we didn't know if it would be even worth trying to solve this in this highly complicated space-time fluctuating general relativity background without knowing if the equations made any sense. In fact, a consistent formulation of fluid dynamics, of viscous fluid dynamics in general relativity, is an open problem in physics and mathematics. There are a lot of mathematicians involved in this since Eckert wrote down the first viscous hydro equations in 1940. Again, I think this indicates that we must revisit the foundations of relativist fluid dynamics and take that as an opportunity to make further progress in the field. So what can we do? So if we go back to fluid dynamics, what do we have? We have your energy momentum tensor, describes how energy momentum is distributed in your field, in your system. You have the conservation law. You can also have, for example, in low energy heavy ion collisions, this becomes relevant. For neutron stars, this is always relevant. You have some baryon, some mass current here. And this is described by a conservation law. And at this level, you have 5 equations of motion, and you have 10 plus 4 variables. There are 10 here and there are 4 here. Of course, at this level, you cannot solve it. There further assumptions have to be made. For example, in equilibrium, just consider there is equilibrium, there is no viscosity, there is nothing. The only thing you should have are 5 variables: temperature, chemical potential, and flow velocity. The flow velocity, even though it looks like it's a 4 vector, it is, but it's a constrained time-like 4 vector here. So it, in fact, only has really 3 independent components. So you have 5 variables for 5 equations. That's good. The equations are non-linear, that's fine. But over the years, in the last 60 years, people have learned how to deal with them. And one thing that is important to say is that these equations, they make sense. They have all of these properties: the well-posed evolution, the solution exists, causality is preserved, if the equation of state is such that the speed of sound is smaller than the speed of light, okay, which is what you would expect. Now, let's go a little bit beyond that and talk about viscous fluid dynamics. The case now where the entropy is produced, right, in this context in relativity. What do you do? Well, that's where the famous or infamous hydrodynamic frames that you see here from the title of this talk show up. Because what happens is the following: the things that really exist in the sense that they come from well-defined quantum expectation values of operators in your system are the energy momentum tensor and the baryon current. The right-hand side of these equations, how you decompose this tensor and this tensor into things that you call flow velocity, temperature, chemical potential, those things are choices. And many people over the years have done many, many, many different choices. This started, as far as I can see, from Stewart in 1971. And Israel Stewart also studied this already in 1979. And the point here is the following: if you can keep track, the quantities that would appear in a viscous system are this A. This A is the dissipative contribution to the energy density. This pi is the dissipative contribution to the pressure. Q here is called the energy diffusion vector. So this is a vector that is orthogonal to the flow, but it tells you how energy is diffused in your system. This capital N tells you dissipative corrections to the number of density of particles or protons that you have there. And this guy is just a diffusion current. So dissipation, as you can see, lead to more terms. You have all these other things to determine. And these fields always dependent on our choice of what constitutes local equilibrium. And the key point that I want to tell you is that this choice is and has always been arbitrary. This only reflects the fact that the hydrodynamic fields are defined in terms of these quantities, which come from well-defined quantum expectation values. But all of these things, temperature, etc., those are emerging quantities that whose meaning become more complicated as if you're in a system that is out of equilibrium. So how do you fix these dissipative quantities? How do you write them down in terms of other variables? So that's the idea that has been pursued for many years. There's the idea of writing hydro as an effective theory using the derivative expansion. And what this means is the following. So imagine that you are in equilibrium. Then in equilibrium, the only variables that you have is temperature, chemical potential, and flow velocity. And there is nothing ambiguous about those. This is all fine. You can always go back to the equilibrium state. This is pretty well defined. However, as you keep now putting viscous corrections, you have these new fields that describe how entropy is produced. And one reasonable assumption is to say that since entropy is not produced when the system is homogeneous, when the system is inhomogeneous, when there are gradients of temperature, chemical potential, and flow velocity, then these fields switch on. So the point is to say that there are no new variables here. The quantities that describe the deviations from equilibrium come from derivatives of the hydrodynamic variables themselves. And a very reasonable approach would be to just list the terms and truncate. So for example, the idea here, and this is really an effective theory approach, you have ideal hydrodynamics. So the full T mu nu is the ideal T mu nu. Okay, so here everything's in equilibrium, there is no entropy being produced. And then you have the first correction that creates entropy. So this thing that creates entropy enters all of these red fields here, and they are derivatives, in this case, at first order. So we have to include the terms that come with first order derivatives here. So here, in this red and this other red here, these will be the terms that will appear with shear viscosity, bulk viscosity, diffusion, and things like that. And another thing that you can see from here is that in this approach, the Knudsen number that I defined right there in the beginning of the talk, the thing that had to be small for hydrodynamics to be to make sense, this thing appears like a coupling constant. So in terms of an effective theory, it's like you have the coupling constant, or even better, the scale at which you're describing your physics, and then you have the first order corrections with respect to equilibrium. And of course, in principle, you can go beyond. So for example, here of order Knudsen number squared, you would have terms with 2 derivatives, and then you can go to 3 derivatives and so forth. Now, people, of course, have thought about this before. I'm certainly not the first one to talk about it. So for example, Landau, if we go back to the famous Landau-Lifshitz books, he already was thinking about this. And then his idea was, okay, let's truncate this expansion to first order in Knudsen number or in derivatives. And then we can just write down the general expressions. For example, bulk has to be a Lorentz scalar. Then there is a coefficient, this is called bulk viscosity, and then this is the expansion rate. For shear, there will be the shear viscosity, and then here, the shear stress tensor. This tells you how entropy is produced when you have a flow velocity going this way, but with a gradient in an orthogonal way. And you also have, for example, particle diffusion, so gradients of the chemical potential. This defined, and that's the word frame that comes up here, what it was called at the time, and it's still called, the Landau frame. So basically the idea is that when Landau writes down these constitutive relations, he's implicitly saying that there is never going to be any correction beyond equilibrium for the energy density, no corrections for the number density, and also that there is no energy diffusion anywhere at all times. Okay, so this defines the theory that you see in textbooks, in Landau's textbook. This has 3 transport coefficients: eta, zeta, and for example, diffusion. It has positive entropy production. The equations of motion are second order derivatives, so in principle, people would be able to solve those, at least at first. And as I said, it defines that energy invariant densities have always the same equilibrium form, and there's no energy diffusion. Now, what happens with this theory? This theory that I call standard relativistic Navier-Stokes theory actually turns out that violates causality. So that's what I see here. And actually, you cannot really solve this meaningfully in general relativity. So in terms of applications, you would not use this. So what's missing? What did Landau miss? What is the thing that we're missing here? Another point here that Deeman asked already is that this theory, this standard construction, actually predicts that thermal equilibrium is unstable. And this is a pretty bad thing, given that in any well-defined system, we imagine that thermal equilibrium should be stable. So this is the bad from the talk. So the kiss of death are really the assumptions made by Landau and Eckhart. And the assumptions were, as I will remind you here, that an observer that is moving with the fluid, which is like the fluid local rest frame, would see no correction whatsoever to energy and barrier densities at all times. And also that there's no energy flux or diffusion at all times. This is really not something that necessarily had to work, but at first, right, in the 1950s, maybe this was a good assumption where, that could be tried. And what happens in this, as you see here, this is really the issue, that at this point, we are making too many assumptions of what constitutes those hydrodynamic frames, or what constitutes the definition of temperature, chemical potential, and flow velocity in an out of equilibrium system. So how do we solve that? So this was solved in these papers, as you can see here, and this goes by the name of first order relativistic hydrodynamics, or generalized first order hydrodynamics. And the idea is very, very simple. It's actually a very conservative approach to solve this issue. You have, in equilibrium, you have your T mu nu and your baryon current, and this will unambiguously give you temperature, chemical potential, and flow velocity. So for example, this nice equilibrium system here. However, as you are out of equilibrium, of course, the energy momentum tensor and the baryon current, they all make sense, right? I mean, these are well-defined things. However, it is not guaranteed that random assumptions that you make of what constitutes temperature, chemical potential, and flow velocity will all be equally good when it comes to fundamental principles, for example, like causality and stability. And what these different hydrodynamic frames are telling you are basically different definitions of what constitutes temperature, chemical potential, and flow velocity. So how do we solve the issue? How do we fix everything here? Very, very simply, we did the following. It's an effective field theory, okay? So hydrodynamics is seen as an effective field theory. So what you do, you define the symmetries, you define the properties, you define the degrees of freedom, and in this case, if we are supposed to write the equations of motion using terms that are first order in derivatives, you see here, there's a derivative of the temperature, derivative of the flow, derivative of chemical potential, instead of just making a random choice and trying to guess from the outset what these variables should be, we take another approach. We let the fundamental properties of the system to guide us to what constitutes good definitions of temperature, chemical potential, and flow velocity in out of equilibrium situations. So that means that you have more coefficients because they parameterize this inherent freedom that you have to describe out of equilibrium systems, but you still have your standard transport coefficients, shear, bulk viscosity, diffusion, etc. Now you may ask, okay, so you have a bunch of coefficients there, but what choices are physical? Well, in the regime of validity of this theory, this effective theory, every single choice that you can make will lead to something that produces entropy. So the second law of thermodynamics is okay, as long as the transport coefficients here are positive. And what we did in a series of works was to find inequalities that is stated basically the following. We found for all of these other parameters here that appeared, all the ones that you don't recognize, we found inequalities that help you constrain and say the following. You still have the freedom. There is an infinite number of different choices that you can make to what constitutes temperature, chemical potential, flow velocity out of equilibrium, but not all of them are equally good. So the good ones you can see from the analysis done in this paper, and this is the good here. There's a well-defined criterion that leads to a set of good definitions for temperature, chemical potential, and flow velocity out of equilibrium. And one example of this is a paper that is published now in Physical Review X here in now in 2022, is a very, very simple theory that you have shear viscosity, bulk viscosity, and you have diffusion, but also you have only 3 other coefficients. And this theory has remarkable physical and mathematical properties. In fact, they are conceptually and in practice much simpler than Israel Stewart theory itself. So what are the properties that this theory has? So the first property, it's causal. And there's a well-defined theorem that we proved here in 2022 that states the conditions for the coefficients that ensure that the evolution is going to be causal. The other property is that the solutions exist and are well-defined. But note that this result here is stronger than you may think. It's not just for the fluids variables themselves. It's also for the fluids and the metric of space-time. So this is the combined Einstein's equations with fluid dynamics together, the whole system of many differential equations, what we showed here and proved through this very rigorous theorem here is that the solutions exist. So you can do simulation, not only in special relativity, as it would be the case for heavy ions, but also for general relativity itself. And also we proved the conditions under which the evolution is stable. So equilibrium states are stable. This is the content of theorem 3. These are all rigorous theorems that you can see here in this paper. It will take hours to explain how they're done, but I'm more than interested in talking to you if you have any questions of how these things more or less are done. So there have been many people that are interested in this, and many recent works have studied this theory. For example, people have investigated what happened to shock waves. Also, there are numerical simulations, for example, here in this paper by Pandya, Mose, and Pretorius. So if you remember, Pretorius is one of the person that first was able to describe mergers of black holes numerically. They picked it up and they have studied what happens, for example, to Kelvin-Helmholtz unstable initial data. So you have some instability because there are some different velocities dividing the boundaries, and they can see how this theory behaves. And it's a very nice simulation they're appearing now. There's also comparisons to holography. So you use the ADS-FT correspondence to solve your microscopic strongly coupled system, and then you compare it to hydrodynamics, and this is done in this paper here. And also in a recent paper that I published with Gabriel Denicol and his student, we investigated how this new theory can be compared, for example, to simple solutions in kinetic theory. And for more details, we can see it in this paper. So I think based on our experience with heavy ions, when we made the transition, almost maybe 15 years ago, from ideal fluids to viscous fluids, of course, in flat space-time, there was really at the same time that there was this paradigm shift between a weakly coupled description of the strong coupling of the quark-gluon plasma to a strongly coupled description. And of course, there were many new insights when he made this transition. We started to understand or try to describe what happens to this nearly perfect fluidity of the quark-gluon plasma. We also, this led to many other investigations between the properties of the initial state involving, for example, gluon saturation and how that is connected to hydrodynamics. And of course, you had to really consider the viscous case for this connection to be meaningful. And more recently, this also led to this concept that hydrodynamics really still makes sense, even far from equilibrium. We are now living the aftermath of that. And by that, for those that know what this has to do, it has to do with these things called hydrodynamic attractors. And of course, this led to many connections to other fields, ADS-FT, cold atoms, and so forth. I think once we start to incorporate these viscous effects, once we incorporate and borrow the technology that we have developed in heavy ions over the years towards the numerical relativity, the astrophysical regime, there are several new problems that I think it'll be useful to understand. For example, we can see how dissipation affects the evolution of this hypermassive remnant of a neutron star, or how viscosity may affect the lifetime and the eventual collapse of the system. And one thing that is much more interesting also, we'll be able to understand not only the equation of state of neutron star matter, but also its transport properties. You see, we gained a lot about our understanding of the quark-gluon plasma once we started to focus on the transport properties. And I think this could also happen in the neutron star emergence scenario. And that will lead to new characterizations of ultra-dense phases of matter. So I believe the inclusion of viscous effects in mergers is bound to lead to some new interconnection between heavy ion collisions and neutron star mergers. And with that, new opportunities and new discoveries will be made. So in conclusion, I think we have signs from the lab and from the sky that indicate that we must really reaccess the foundations of relativistic hydrodynamics. I think this is the time that we can do that. There's new techniques, there are new techniques that allow us to do this type of study, and I think this is the time to do it. The new constraints that I showed you here reveals that merging this initial state physics to hydro still has some fundamental issues to be figured out. I mean, these appeared in terms of causality violation, but I think this is really the key point, how to merge initial state to hydro, that we now can really focus on. And towards the second part of the talk, recognizing this inherent freedom in what really constitutes the hydrodynamic variables out of equilibrium led to a new formulation of hydrodynamics that I described here. That really solved, I think, in my opinion, this 80-year-old problem in physics and math, which is, what happens to a system out of equilibrium in general relativity. And we're really excited about the consequence of that finding. And I think we are now living in a new era defined by the synergy between heavy ion collision and neutron star mergers. And I think it's really bound to lead to new fundamental questions and discoveries. So for example, now that we understand how hydro behaves in GR, maybe we can think about crazy things like turbulence in general relativity. Who knows? There are many things to do. Thank you so much.
Well, thank you, George. Thank you for the very, very stimulating talk. So I think we have some time for further discussion question, and then I see Dima already raised his hand. Please go ahead, Dima.
So let's go back to, let's say we have neutron star
Yes.
or neutron star merger. And in this merger, it is actually quite likely that you would encounter some kind of phase transition, because if you go with densities up to, let's say, 6 nuclear densities, and temperatures are not very high. So meeting, unlike heavy ions, actually, meeting a phase transition or some spinodal region is a likely thing to happen.
Yes, that could happen, yes.
Now, in spinodal region, your conditions are going to be violated for sure.
Yes.
You are going to have speed of sound square at less than 0. And you are probably going to have to introduce some kind of surface tension, some kind of gradient terms. What will happen to the causality conditions?
Excellent question. I have no idea. But the one thing I know is that nature has already figured that out. Because for sure, when whatever this happens in nature, causality is not violated. So I have no idea. And this is a fantastic question. I have been thinking about that. The first thing I did was to read some older papers from 10 years ago, where people actually proposed this very nice thing that you just mentioned. For example, you can shift the pressure by some gradient of the density, right? So there are several cool things to do there. I don't know how to do that in a relativistic consistent manner yet, but you touched on a very, very sore point that I for sure don't know how to do it. And I think it's, I don't think anybody knows how to do it.
Well, I think Scott Pratt thought about it. Scott Pratt published some paper, but he himself says
not in the relativistic
it's not
regime.
finalized.
Not in the relativistic regime, for sure.
No, in relativistic regime. This is what he talked about.
Non-relativistic, yes. Non-relativistic, yes, of course. And those are the papers.
Relativistic,
no,
like high speed.
For sure,
but,
for sure.
Okay, we can discuss that.
That's not solved. I mean, I can prove to you mathematically that the simple extension of what was done non-relativistically will not work relativistically. So I haven't seen. Yeah, I haven't seen what Scott did, so I cannot comment on anything he did. But I can certainly comment on the simple generalization of what was done before, and that is not really going to work.
Okay.
Okay, Jennifer, you have a question? Please go ahead.
Thank you. George, thank you. That was a wonderful talk. So I have a question about the previous question. I sort of missed in the very beginning. I could understand for neutron star merger that it's definitely possible for a phase transition to occur, but why did you both sort of say that it was likely? I don't understand.
Why am, is it a question to me or is it to George?
Well, to both of you.
Dima, you can answer first.
So let's say when you go to very high density and low temperature, there is a color superconductor predicted. And for that, there is definitely a change of symmetry, so a phase transition has to happen there at very high density and low temperature. This is not the region you are reaching by heavy ion collision. So, well, that's why I'm saying that at least that phase transition is something that you would like.
I can comment on that. So this is something that brings back my old days as a grad student. So I actually worked on color superconductivity as a grad student. Yeah, so what Dima is saying is that at least think about asymptotics, right? If you are at infinite densities, forget about temperature, but infinite densities, the ground state of nuclear matter will be written in terms of deconfined degrees of freedom, you know. It is basically understood that at sufficiently large densities, you're going to have pairing between the quarks. So there's going to be color. It's a color superconductor. Just like you have a standard superconductor for electrons, now you're going to have a color superconductor. And the attractive interaction that creates the instability on the Fermi surface is driven by just a simple one gluon exchange. So this is something that is understood, at least since like 20 years ago. But of course, the problem is we don't live and we're never going to access infinitely large densities. So the question is, at the densities that Dima mentioned first, 6 times nuclear saturation density, will color superconductivity already appear? I don't know. What kind of phase of matter is there? I don't know. How do you describe very excited, very dense hadronic physics in that case? I don't know. In that case, the standard phase, which I mentioned there was a color flavor locked phase in that case, is not really guaranteed to be the preferred phase at not asymptotically high densities. So there could be some phase transition depending on the type of matter that you have, on the type of pairing between the quarks that you have. So even that is unknown. But one thing that you should keep in mind, and I think that's the main message, is that it is possible, and there are several models that do support the presence of some interesting phase transitions at high densities. Whether or not we're going to see that, I don't know.
This makes a lot of sense, and I'm a big fan of diquarks as Cooper pairs. So is there a paper that actually showed at infinite densities, you're sort of guaranteed to get this, not even a color flavor lock, but a color super? Really? Is it Wilczek?
Yeah.
Who is it?
It's not just Wilczek. There were a few people involved. I can send you, if you want, I can send you the, if you can quickly send me an email afterwards, perfect. I can right away send you the references that I think are relevant.
Thank you
and you
so
can
much.
go from there.
Thank you.
Sure.
Okay, any other further question, comments from the audience?
Can I ask one more question?
Yes, yes, go ahead, Jennifer.
So George, way back in the beginning of your talk, when you were saying that nature is much more complicated, and that there are certain regimes in which this Knudsen number is actually kind of big, and but it's still, we can still treat the system as hydrodynamically.
Oh, we think we can.
We think we can. Thank you.
Yeah, that's what we are doing.
Okay, so in that slide, there it is. Yes. So in that slide, the unavoidable quantum fluctuations. So you said these quantum fluctuations could be the size of the proton. What is fluctuating into what? Yeah.
So think about the two nuclei coming in to collide. Okay.
Okay.
So of course the nuclei are, they have not only protons and neutrons, but within the protons and neutrons themselves, you have quarks and gluons, right? Those are quantum fields. In fact, every single thing here in this sheet of matter, I mean, I'm trying sort of giving the impression this is a sheet because it's highly Lorentz contracted when before the collision, right? Because it's coming at very, very large velocities. And then of course, so imagine that you have your neutrons and protons here. Those are quantum fields. So there are always quantum fluctuations, okay? And there are quantum fluctuations at different scales. There will be quantum fluctuations associated, for example, to scales of the size of the proton itself. So if you could think about the proton just like a little ball, and the proton has a size of like a Fermi. So it's like a fluctuation of the size of one Fermi here in my hand, right? So these will be associated with the confined scale. But of course, so you also have quantum fluctuations defined at much shorter wavelength, which will be related to deconfined degrees of freedom, quarks and gluons. All of these things are there. Right?
But George, fluctuations, like I'm used to people saying things like, okay, there's a fluctuation in the separation distance in between two nucleons, a quantum fluctuation to the separation distance, or a quantum fluctuation of relative momentum. So I guess I don't understand what is the quantum fluctuation? Is it a spatial thing?
No, it's just think about the wave function. How do you describe the wave function of a nucleus? Okay. Mm-hmm. So the nucleus, so it's a wave function, okay? So it's a quantum system. It's not a little point or a little ball that is, has a well-defined position and momentum. This is a quantum system. There is a wave function that describes this. Yeah. And within this wave function, you have protons and neutrons, which are also quantum things inside.
Yeah.
Okay. So, and also within each one of these protons and neutrons, we have quarks and gluons.
Yes.
So there is fluctuations of everything everywhere. Whether or not these are relevant for which phenomenon in heavy ions, that's the key. Because of course, you would think that fluctuations defined at very tiny length scales, like really, really inside of the proton, right? Very, very, very tiny things, much smaller than a Fermi. Those things in principle are there, but they should not really affect what happens to hydrodynamics, because hydrodynamics is supposed to describe the large scale structure, right? You know, things of the size of the nucleus, or maybe a little bit smaller, but it's not there. This is not a description to describe every single possible little thing that is in there. The same way of the air here. You see, there's the air here. Hydro will describe how there is the macroscopic motion of the matter here, but it has no idea what's going on with the little spatial fluctuations of the positions of the little molecules. Okay.
Excellent. Thank you.
Okay, maybe let me have a final comment on this. You know, of course, we all know maybe the ultimate ideal solution is to do quantum transport, right? Which is, of course, impossible. And then you take some kind of approximations called semi-classical approach. You trying to solve the Boltzmann equation. But then again, for a complicated system like neutron star merger, even heavy ions, that is also too complicated, you know, computer intensive to do. So you boil down to hydrodynamics.
Yeah.
And then, of course, this is a big approximation. And then in particular, when you're getting away from equilibrium. But but instead of doing this, what you call you know, derivative expansion to describe to some kind of non-equilibrium, but in most of other approaches that people have taken, like a mixed approach, like short wave and long wave length. If you have short wave, like a long wave length, you use hydrodynamics when density is high, and then but for short wavelengths, when you're out of equilibrium, you simply took like a transport, like, you know, transport approach, and you can combine this together, right?
Yes, of course, yes. Of course, the combination of those things is very complicated, especially in the relativistic regime. But you're right. The thing that I'm thinking about here, especially for the neutron star case, I'm just trying to understand the very first deviations from the standard or ideal hydro description. I'm still here, for example, when I write down these complicated equations in GR and everything, I'm still trying to describe long wavelength phenomena. They are influenced by viscosity, right? And the viscosity, of course, is determined precisely by these microscopic degrees of freedom that we could be describing using different approaches. But here is just for the hydro itself. In a more complicated thing, for example, in a merger, you have several other different things. You would have the hydro description, besides the GR, of course. You have the hydro description, you have electromagnetic fields. Those are very, very important. And how these things are distributed in your system make a difference. And you also have other particles, for example, neutrinos. They're not really a hydrodynamic fluid. Those are really
that's why I think in many many like simulations, people don't just use hydrodynamics. They use a mixture of hydrodynamics. Sometimes use transport, and sometimes use you know, electromagnetic, you know, equations too, right? And there's also emission.
Yeah, I agree. This you see, I think the contribution here is, of course, first the conceptual thing, like how did this make sense and everything, but how I think this is going to work in the future, it'll be the following. So for example, the bulk viscosity that I mentioned here, that bulk viscosity actually has nothing to do with the strong interactions. It's a bulk viscosity induced by weak interactions, because as the density varies, the amount of neutrons and protons varies, right? Because the things can undergo beta decays. And that you can show that when this process is slow enough, you can describe this in terms of some effective bulk viscosity. And that's the thing that I was talking about in the phenomenological part. But of course, if you are under conditions where the things are not slow enough, then you cannot really describe this as hydro. It will have to be some other microscopic description. But it will be a hard thing, right? Because, for example, you would have to solve the Boltzmann equation of full GR, dynamical GR simulation. These are hard things that people have managed to solve under certain conditions. But I think the value of the hydrodynamics is to first understand how this can be meaningfully extended in GR, right? So how you could solve it. And maybe it will provide a good description of phenomena at very long wavelengths, right? Not, of course, everything, but just as it should be. I mean, this is an effective theory. It should be applied in the regime that it makes sense. I think that's what we're trying to figure out.
Yeah, yes. Okay. Well, I think if there's no further questions, and then well, we have been over like almost like 20 minutes now.
I see people leaving already, and I'm fine. Maybe like I would still ask a question, but it's, I don't know, consider a private conversation.
Oh, okay. We probably let's thank Jorge again,
let's thank Jorge.
Whoever want to stay, we can continue to discuss. Okay.
Yes, I can stay. Thank you. I can stay here for another minute or so. I mean, it's kind of late still already for us here. But it's but Dima, go ahead. Thank you, Xinyan.
So since it is private, I guess the recording is stopped. So
yeah, let me stop.
The question is basically the same that I asked a year ago on a similar talk.